Hey gang, I'm here to spend a few minutes with you talking about electron configuration exceptions. And I want to really clarify that we're not really dealing with exceptions here. It's all energetically favorable situations. So if we understand one simple rule and how to spot it, you can avoid making mistakes with some transition metal element electron configurations. One of the primary examples that we deal with in teaching kind of this exception is with copper. And when a student writes a configuration for copper, he or she will typically say, well, okay, 29 electrons, the first two go in the 1s, and then the next two go in the 2s. The p orbitals, oh wait, those are degenerate, so there's 3 degenerate orbitals, so it holds 6. And then the 3s and the 3p gets completely filled. And then, oh yeah, my teacher taught me the diagonal rule, so I know that instead of the 3d, the 4s gets 2 electrons before the 3d gets 9 more. And the student turns the homework in feeling confident. The teacher then takes a look at that assignment and says, oh, you know what? This is actually wrong. It's an exception, and the ending is actually 4s1, 3d10. Now, this can lead the student, when they get that assignment back, to be like, what in the world are you talking about? This is what you taught me using the diagonal rule. Why isn't it 4s2, 3d10? Let's look at it briefly through the lens of energy. Remember that one of the big reasons why we write electron configurations the way and in the order that we do is to follow the Aufbau principle. And the Aufbau principle states that electrons are going to try and maximize their attraction to the nucleus. Nucleus is positive, electrons are negative, they're going to be attracted to one another. And fundamentally what that means for us is they're going to go to the lowest energy state that they possibly can. So let's do the same critique now looking at the incorrect configuration and then compare that to the correct. So the incorrect configuration, we put electrons in the 1s, the 2s, and the 2p. So far, so good. We haven't really made any mistakes yet. The error comes when we completely fill the 4s. Now, for this region here, I want you to notice something. That difference in energy between the 3D and the 4s, very tiny. Here's the additional information that can be helpful. When you compare the 3D, which has 5 degenerate orbitals, to the 4s, which only has one orbital, it's going to be a more energetically favorable situation for the 3D to be either halfway filled or completely filled. So either have 5 electrons or 10 electrons. Now, we can't always make that happen, but in this case we could, because for copper, we could promote an electron from the 4s and move it into the 3D. Now that would leave the 4s halfway filled, but that's not the worst case. What we've drawn here is actually a higher energy state than what would be possible with the correct version. So let me show you the correct. Now for the correct configuration of copper, the first and second energy levels, our configurations don't change. Everything fills the way we had previously. Now the change happens in this same region, so in this region right here. Instead of completely filling the 4s, it only gets 1 electron. And that additional electron that we would have put in the 4s goes to completely filling that large 3D. Now we can understand that that adds some stability, because if you look at the third energy level, which is the sp and d orbitals, now that energy level is completely filled. That falls a lot in line with what we know about noble gases, which all have completely filled valence shells, completely filled energy levels. Okay? Even at the expense of having a slightly lower energy 4s being halfway filled. It might be helpful if we look at another example where I think it's even more obvious. So we know that electrons are going to repel one another, and that's really the focus of how we can explain the exception of chromium, which again, not really an exception. Okay? If we were to write out chromium's configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. We turn it in, we feel confident about it, and then your teacher says, no, 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 I'm sorry, that part at the end, not right. In reality, it's 4s1, 3d5. And instead of being perplexed, which it's easy for us to do with a problem like this, let's look at it from an energy standpoint again. So remember I said that we need to think about electrons here. And electrons, we have to remember, are negative particles. If we put electrons close to one another, they're going to repel. So we can make sense then out of this corrected configuration for chromium by understanding that, okay, the 1s, the 2s, and the 2p, this is getting to be old hat for us. There's no exceptions there. 3s feels like we would expect it to. 3p feels like we would expect it to. Now we're going to pay attention to this region here. Remember what I said before. Having a degenerate set of orbitals, halfway filled or completely filled, is an energetic benefit to the atom. So what that means for us is that instead of having the 4s completely filled, we're only going to half fill it. And take that additional electron and put it into the 3d. Notice because of this configuration, now the 3d and the 4s, they're all half filled. And the benefit there comes from minimizing repulsion between those electrons. Those are two examples. You'll notice that anything that's in the same group as chromium and copper will exhibit very similar patterns of what you might consider to be called exceptions. But in reality, they're not. It all has to do with creating a most stable, energetic configuration. Hope this was helpful. Have a great day.